Do you trust your RAID array with your data? You shouldn't. RAID is an acronym that means Redundant Array of Inexpensive Disks. The assumption is that if you have stored your data on a set of hard drives, the data is stored in such a way that if a drive fails, you lose no data. And in case you didn't know, RAID is no substitute for a backup. In fact, I'll say it now, if you work in the enterprise and you want to store 1 gigabyte of data, you're going to need to store 4 to 8 gigabytes worth of space in total to be reasonably assured that that you were not going to lose that. That said, at a minimum, you need 3 completely independent copies with room enough for spatial and temporal snapshots with differences of the data. So back to RAID. RAID is rarely, as simple as it's made out to be. So what's being tested in this video? For me, the priorities of a RAID are: don't allow the data to become corrupt, to experience bit rot, in other words. The data that you put on the array should be the data that you get back from the array, even after a hardware failure. Replacing a failed drive should work, and not corrupt the data as a result of the drive having been replaced. Corrupt data ahead of outright drive failure should be detected, reported, and corrected. The RAID mechanism really should not rely on just the mechanisms of the mechanical hard drives, but all too often that's the case. And the performance should be reasonable for the number of spindles involved. And so what we're really talking about here is that your data integrity is the most important thing, and then everything else, speed and everything else that follows that, is sort of the lesser important metrics. I mean, sometimes you see things on the internet that's like RAID 0 SSDs for speed. Well, that's insanely dangerous with your data, but if you want speed, I guess that's what you can do. All right, so let me start by explaining RAID 1, RAID 5, and RAID 6. You can probably skip over this part if you already know. Okay, so RAID 1, typically that's a simple mirror. You have 2 drives set up such that the same information is written to both drives. If one of the drives dies and goes offline, you can read the data from the other drive. It's basically just a mirror. When you have a write, you write it to both the drives, and if one of the drives dies, it's on the other drive. Makes sense, straightforward, that's easy enough. RAID 5 is a little more complex. In a 3-drive arrangement where you've got 3 drives operating in RAID 5, any one drive can die, but how does that work exactly, that any drive can die? Well, the mechanism for this is that the data is split into at least 2 chunks, and we'll get more into that in a second. A special type of mathematical operation is done on those 2 chunks of data, and it's the type of computation is called a parity computation. It computes the parity. Essentially, the parity is just the mathematical difference between the 2 blocks of data. It is chosen this way in order such that if one of the 2 chunks is lost and you still have the parity, the lost chunk can be recomputed. So if you have chunk 1 and chunk 2, chunk 1 is lost, you're able to look at the data in chunk 1 and the parity and recompute what the missing chunk is. That's basically all that is. And so RAID 6 is sort of an incremental improvement on RAID 5 in that you have an additional chunk for parity. Now, for like 3 drives or 4 drives, I mean, you could do a 4-drive RAID 6, but it really doesn't matter. We're talking RAID 6 is you see more when you've got like 6, 7, 8, 9 hard drives, because people that were running, RAID 5 with like 5 or 6 or 7 hard drives would experience multiple failures just because there's so much data stored on modern hard drives, terabytes and terabytes of data. And so like one drive would die in a 5-drive array, and then when they replace the drive that died with a blank drive, and then it's reading all the stuff off of all the other drives, there would be another failure. And so RAID 6 gives you a second set of parity so that you can recover from a 2-drive failure if necessary. Just for the sake of completeness of the definition, let's suppose that the RAID 5 that we're talking about was not 3 disks and instead it was 5 disks. The data would be split onto 4 chunks, plus you would have a parity chunk. Now, some people say that you have 4 data drives and 1 parity drive. This is a fine way to think about it, but it's not really what's happening under the hood. It's not really what's happening underneath. In reality, all modern systems that take parity data and spread it evenly across all drives in a given pool. It is accurate to say that in a 5-drive RAID 5 array, you would have 4 drives worth of space, with 1 drive's worth of space going to parity. But that parity is not actually all on 1 disk. It's spread evenly across all of the disks. So just something to keep in mind if you're super pedantic. Now, some of the systems that we're going to look at are not exactly RAID 1, RAID 5, or RAID 6. It's a different kind of RAID, and that's sort of the point here. Now, what I've told you about RAID arrays, you might already know. I've given you a hint about the doomsday scenario that's coming up, though, and that is what happens if you don't necessarily have a drive failure in one of these drive pools, but instead the drive fails in such a way that it's lying and returning bad data. So if you've got RAID 1, if you've got a mirror, and one of the drives in the mirror has gone evil, and it is returning data, but it's returning incorrect data, but it's not otherwise really reporting that it's failed, what does that handle? What happens in that situation? Think about that, and we'll come back to that in a second. So before we get into that, let's talk about the different kinds of things that we're going to test. Now, when you get right down to it, we are going to be looking at the same things here really, I mean, between the hardware and the software options and some of the other stuff, you could say that it's really an apples to oranges comparison. And that's really just because this type of technology is in a transitionary phase. The sort of the RAID system, the old guard, like the way that it used to be done with RAID, is really kind of out the window for some different reasons that'll make sense later. But it is a fair statement to say that some of the stuff we're looking at, we're really sort of comparing apples and oranges. But that's okay, because this is something that, like when I'm doing an audit, when I'm doing an enterprise audit or something like that, this type of misunderstanding just comes up over and over again. It's like RAID is not a substitute for a backup. RAID is not bulletproof in terms of some oddball situations you can get into. A drive failure is the most expected way that you're going to have a problem, but you can have sort of a black swan event where something happens and it was sort of an unpredicted type of failure, and then you get into uncharted territory and it's just really bad. You run into this in the enterprise all the time when you've got really expensive stuff you got to take care of. You're going to have these really weird edge cases and it's not going to make any sense. In the past, the way RAID has worked is that you have a piece of hardware, or if you're very unlucky, a piece of software, would take all of your disks and present it to the operating system, or present it to whatever, as one huge pool of storage. And that piece of hardware, or that piece of software, if you were unlucky, would be operating behind the scenes underneath the operating system to make sure that failures were handled and that errors were corrected and that sort of thing. And really, when we're looking at some of the more modern approaches to RAID with file systems like ZFS and BTRFS or ButterFS on Linux, those file systems really need access to the hardware that underlies the array. There's not really a hardware controller that is sort of managing that aspect of it. It's sort of managed in software, and so it is a software RAID solution, but it's not a ghetto software RAID solution. It's a software RAID solution that's typically better than a hardware RAID solution, but you've got the overhead that comes with that, and so it's kind of a trade-off. If you've worked with enterprise storage systems, you probably already know that RAID is basically an obsolete technology, and you probably have a SAN. Well, what's a SAN exactly, for the purposes of this video? And we're not really going to get into SANs much here, but it's just something to keep in mind. A SAN is really a server that presents a pool of storage on the network, and it typically does things that are more advanced than simple RAID. You've probably heard of a NAS, that's network attached storage. Typical NASs do simple RAID, but they don't do some of the advanced things that we're going to talk about. They don't really do things to protect you against bit rot, because remember, bit rot is the most important thing that we're talking about in the context of this video, in the context of long-term data retention, in the context of not losing your data, not losing the crap that you put on an array. Typically, a SAN will offer up its storage to a server as an iSCSI target or NFS or other proprietary protocols, and so it really takes care of the underlying mechanism. It doesn't just present, it actually does a lot of work between the actual storage and data retrieval and data retention. There's a lot of stuff going on there, which is like ZFS and BTRFS, but it's not really like a hardware RAID controller like a Dell PERC or an LSI controller or a software RAID controller. So essentially, RAID, as we've defined it for RAID 1, 5, and 6, relies on hard drives to self-report that they may be dying, or that they may have bad data, or that they're failing, or whatever. There are two types of disk interfaces that are popular right now: serial attached SCSI, that's SAS, and SATA. Now, SATA is probably the one that you're familiar with. SAS is what's more used in the enterprise and servers, like medium end servers and on up. Sometimes you'll see SAS in nearline devices that are like SATA drives. They're really just souped up SATA drives. You see those in the enterprise. Typically the difference between SAS and SATA is that SAS is considerably more expensive, but also SAS has better built-in error detection and error correction. And they've got, there's stuff in the drive to try to do sanity checks and error correction much more so than you run into with SATA drives. So SATA in the enterprise is still a thing, still totally happens. But, you also see SATA used in large installations. Companies like Google and Facebook and those types of companies are using really, really cheap, pretty much the cheapest they can get, SATA drives, and they really rely, not for everything, but for a lot of things, and they rely on their software stack to correct errors with that hardware, because conservative industry estimates put that hardware at 10 times less reliable than the equivalent SAS or enterprise grade gear. So that's something to keep in mind. Now, it's also true on the SATA side of things that vendors are aware of this, and they are segmenting their market with multiple different SATA drives that address some of the shortcomings of SATA. And so like Western Digital and Seagate each have different classes of SATA hard drive, like, oh, this one's for video storage, oh, this one's for NAS, this one's for whatever. And typically the firmware and error correction and some of the other stuff there has been tweaked to be more appropriate for each of those use cases, and then they charge appropriately. So whether or not that's worth it, left as an exercise to the reader, but something to keep in mind. Now, for our videos, for our purposes, what are we actually going to look at? It's like, okay, we're going to take a look at a few different things. We're going to look at MD on Linux. This is Linux multi-device. It's, real good name. This is a software RAID solution, and this is RAID in the traditional sense. This is the particular setup we're going to look at is RAID 5 with 3 hard drives, and we're going to format this RAID 5 file system with ext4, the ext4 file system. We're also going to look at BTRFS, or sometimes it's called BTRFS. We're looking at RAID 1 with BTRFS because RAID 5, RAID 6 with BTRFS is not really well supported yet. They literally just checked in some changes for kernel 3.19.1 that is supposed to enable RAID 5 and RAID 6. It is still not exactly stable, and it is very, in my opinion, very far from being ready for production use. That said, I know people that have been running it for years. I have not been running it for years. I've been running it for 6 months probably. RAID 1 is basically okay, but anything other than RAID 1, I think, needs to bake a little longer, but they're getting close, and BTRFS is sort of promising. And we'll talk more about what BTRFS is in a bit and what that means, that kind of thing. We're going to look at the Dell PERC 6. It's a hardware RAID controller. I thought I had an LSI controller handy, but I don't. So if anybody wants to send me one. That'd be great. The PERC 6 is a hardware RAID controller. It's an 8-port SAS controller. It has an ARM controller. It has, I think, 256 megs of RAM. It also has a battery backup unit. It has its own built-in battery to keep the RAM powered. And we'll talk more about why that's needed in a minute. And then we're also going to look at ZFS on FreeBSD. Now, this is a 3-drive RAID Z1 setup, this is similar to a RAID 5 setup, but again, this ZFS is aware of the drives, and so it's not quite it's software RAID, but it's not software RAID in the traditional sense. It's software RAID that is designed with multiple drives in mind. It's designed to have direct access to multiple drives, whereas the older like MD software RAID is really just a dirty hack. Like, no one should be running software RAID in any kind of environment, even like a small business environment. If you just have Windows Server and it's like, oh, let me click on 2 hard drives, make it a dynamic volume, turn that into a RAID 1. No, please do not do that. No, that's instant fail on data integrity, on a data integrity audit. It's just RAID 1, honestly, if you had to do it, RAID 1 is probably the only thing that would kind of halfway be okay. But like the software RAID 5 on Windows, you're asking for trouble. And unless you've got a hardware RAID controller with an ARM microprocessor and a battery backup unit, you don't want to be running. It's bad news. It's just, trust me. So how are we going to do the testing then, is your next question. I was like, well, glad you asked. We have some scripts that we've set up, and we've published those on the website. Those scripts are configured to generate 500 megabyte files that are filled with either zeros or random gibberish. Now, if you're going to fill it with random gibberish, it's going to come from dev/urandom. Dev/urandom, you can get 10 to 50 megabytes per second. of random data. So it's not going to be the fastest thing in the world if you want to fill it with random data for testing purposes. Honestly, it's fine if you want to use nothing but 0 filled files for these tests. So we're going to fill the drives with 500 megabyte files that are basically completely empty files. And we will then compute the MD5 sums of all of those files. So after we've computed all those files, we're going to read all those files back in. Now, here's a hint: all of those files should have the same MD5 sum, and they will, because they're all empty and they're all identical. So there you go. Now, once we've established that, once we've got, the list of files, the number of files, the list of file to MD5 sum mapping, we are going to do some other stuff. Why are we making an MD5 of every file? Well, we're going to introduce corruption on the file system. We're going to corrupt the array just a little bit, and then we're going to reread all the files and see if any of the files have changed. An MD5 is a mathematical hash of the entire contents of the file. So that 500 megabytes is taken and compressed down to just, a very short character string of, a hexadecimal string basically, that is representative of the contents of that file. If the contents of that file change even a very little bit, it will dramatically change the MD5 sum. The MD5 sum will be completely different. So if we introduce corruption and then we reboot the array and the array is up and running and the array is like, hey, everything's fine, and then we reread from the array those files and that MD5 sum changes, we know that we've been successful in introducing bit rot. Now, normally this type of corruption that we're doing, it wouldn't occur naturally, but over time, with the aging of hard drives and magnetic fields, and just you turn the computer off at the wrong time, random crap may end up being written to the drive in a similar way. And so what we're doing is really sort of simulating the passage of a large amount of time. It would not be unusual to have this type of corruption that we're going to introduce on one of the drives in the array for a drive that has been, operational for a couple of years. Or some drives have onboard memory. The onboard memory is not error correcting, and so this type of memory-based error, if there's a problem with that buffer memory on the physical hard drive controller on the hard drive, then you will see some corruption like this potentially. So this is not an unreasonable test. So if you want to repeat the tests, please download the scripts from the website, post on the forum.techsyndicate.com. If you have any questions, there's an associated forum post that goes with this article. So you can do your own tests and see if see how your own controller works for this. Once we've done that, and we've got our results from whether or not the array was able to recover from that, we're going to pull the drive from the array that we fiddled with completely and just see if the drive continues. Now, when we take the drive out that had corruption, our suspicion is that the drives that had a bad MD5 sum will become corrected probably, because when the drive is no longer reporting faulty data, just not reporting at all, the parity mechanism will work like it's supposed to. The problem is that with MD and some of the other stuff, the parity mechanism depends on a drive not being there in order to recompute it. If all the drives are there and you go to read something and the parity's inconsistent, it doesn't know which drive to trust. So you've got in a 3-drive RAID 5, you've got a 50-50 shot of it returning the right data. So just something to keep in mind. Now, before I mentioned the hardware RAID controller, and it has its own battery. Well, why is that? Well, this is a convenient way that we need to talk about something else that happens with RAID arrays. That's called the write hole. So when you have a block of data that you're writing out to your array of disks and the power's pulled, what happens? Well, it's a mess. When you've got that block of data and it's due to be written out, it may have been written to some of the disks, but it's not guaranteed to have been written to all of the disks. In an unexpected power failure event, the drives are going to lose power at different times. And so what normally has to happen is the thing to be written goes into memory, and then the controller says, okay, let's write that out. And then it'll go and it'll write it out to disks. And then when all the disks say, okay, we're done writing that, all of the disks, then it'll flush it from memory. And so this is a hardware controller. This is also why you really need a hardware RAID controller if you've got a file system, unless you've got a file system that can deal with multiple physical devices. So you've got your hardware RAID controller that's got memory on it and like a buffer. And so if it loses power, it doesn't know of that, you know, block of stuff, which things were written to disk and which things weren't. Without that memory unit, you know, in a 5-drive RAID 5, 2 of the drives could have been written and the other 3 not. And so when the computer boots back up and it goes to read, it's going to have some of the information, but not enough, and certainly not enough to reconstruct on the parity situation. And even if it did have enough to reconstruct on the parity situation, it's that situation where you've got some data corruption and it doesn't know which drive to trust because it's looking at all 5 drives and it's like, well, did the write finish? Yes or no? You don't know because there was data, you know, on the drives that didn't actually get written. And so if the controller looks at it wrong, then you're just going to get random gibberish back. And so this is a bad situation. And this is why pretty much any server of the last 5 years that has anything other than the crap RAID controller will have a battery backup unit inside it for the memory that's on the RAID controller, because the controller has to be sure that everything was written, either none of the disks were written or all of the disks were written. And so when the server boots back up, the next time it gets power, because the battery just keeps the RAM powered, it doesn't keep the drive spinning or anything like that. The next time the server's powered up, the controller boots up and says, oh, there's crap in RAM. Okay, let's just rewrite everything. And so it'll, you know, just start over for all of the disks. And so the first disk or 2 or 3, or maybe all of them, would have that thing that was written in memory, and the controller will just write it again. It's not a big deal. And then once all the drives have confirmed that they have written it, then it will release that from memory. This is a pretty good system. It basically ensures that the array is consistent and you don't have a problem with the write hole. So the question that should be burning a hole in your mind is, well, wait a minute. We've got MD on Linux, which is used everywhere. What does it do for the write hole? The answer is nothing. It does nothing for the write hole. It's a bad situation. If you reboot a Linux machine and it's an unclean shutdown, meaning that, you know, it's rebooted unexpectedly and you haven't shut down the MD array, it's going to start resyncing all of the parity. And so when you reboot, you're going to have that situation where it's UU underscore, like we were seeing when we were building the array. And literally the drives are being reread and the parity is being recomputed and distributed throughout the array. The entire thing is lost. And so if the computer's shutting down and shut down unexpectedly and one of the drives in the array goes haywire, you've immediately lost all of the information on the parity, because as soon as the thing comes back up, it immediately starts overriding it. And so if you get into a situation where, oh, the data's corrupt, maybe if I had the parity, I could fix it. Can't do it. The parity's gone because it's been overwritten, because it might have been dirty. Some of the parity might have been dirty. So the only option is to just rewrite everything. So that's what MD does, which is sort of, it really can't do anything else without without the memory. It's not a good behavior, but it's the best behavior that it can do given the situation. And that's why you always want to run, even if you're running BTRFS or ZFS, you really want a battery backup, like a 110 volt external battery backup that will notify your machine to shut down when there's no external power. Because when you're running BTRFS or ZFS, there's not an option really for a battery backup unit on the controller, because those file systems expect direct access to the disk. And we'll get into more about why that in a minute. Let's talk about some of the differences of BTRFS, ButterFS, and ZFS with a traditional RAID system. It's not exactly the same. It is kind of an apples to oranges situation. And it's important to understand that it is a little bit of an apples to oranges situation. BTRFS and ZFS they're file systems, but they're file systems that are RAID aware. And so it really blurs the lines between RAID functionality, which is taking a bunch of disks and presenting it as a large empty volume on which you can put any file system, to BTRFS, which is a combination of file system and way of dealing with redundancy. It's sort of two things rolled into one. And the reason for that is because there's a lot of overhead to it, and with old computers this would have been a bad idea, but with modern computers where they're so fast, maybe it's a thing. And ZFS, good lord, takes 8 gigabytes of RAM just to get started. And part of the reason why is because it can deal with all this situation. You don't have to deal with this in hardware. So because of this overhead, if you've worked on this kind of stuff in the enterprise before, this kind of overhead is the type of thing that you see also on a SAN. So a SAN will help you prevent bit rot. A SAN will do things for you a lot, honestly, a lot of commercial SANs run ZFS just under Solaris, not FreeBSD. But that type of file system is important because it provides parity and it provides redundancy, and it is aware of multiple disks running underneath it. And the file system is designed not to really trust the hard drives. In ZFS's case, it trusts the RAM and the CPU and the motherboard. And so that's why ZFS, all the forums are like, oh my God, if you're using ZFS, you've totally got to get error correcting memory, because ZFS assumes that if it encounters an error, it's because there's a disk lying, not because there's bad RAM. And so ZFS making that type of an assumption will be very bad news for the integrity of your data if it was actually a RAM problem. So keep that in mind. So these types of functions are really also the same types of functions that you see on a SAN. And so a lot of the time, not BTRFS, because BTRFS is way too new, but ZFS, where it's older and more mature, runs on Solaris and other proprietary file systems, you will see those on SANs. And this is some of the stuff that they're doing under the hood. Now, SANs also do a lot of other really fancy stuff beyond just this, but this is why SANs are so much more expensive than NASs. I mean, it's not unusual to have a SAN that's $250,000 or more. Even inside a company with only 500 to 1,000 employees, it's not unusual to spend $150,000 on a SAN. I mean, a SAN does a lot for you in terms of integrity and in terms of the whole statistic that I was telling you about. Oh, if you want to store a gigabyte of data, you're going to have 4 to 8 gigabytes worth of space. SAN can help maybe sort of kind of fudge that a little bit, because it'll store deduplicated blocks of data. It will store differential snapshots, so that you're not, if you've got 5 copies of a file and that file's a gigabyte, you're not necessarily storing 5 gigabytes worth of information. You're storing the first gigabyte and then the differences for the second file and the differences for the third file, and sort of under the hood, it's doing all this kind of stuff transparently to make it like you've got 5 1 gigabyte files that are a little bit different from one another, but really under the hood it's just one 1 gigabyte file and then some very small difference files. Now, there is one important piece of terminology between the SAN and BTRFS and ZFS, and that is background scrubbing, or just scrubbing. Scrubbing is generically defined as a function of the file system that, when it's not busy or periodically, it will go through and look for corruption, or at the very least inconsistencies. It may not rise to the level of corruption, and it will correct those instances of corruption. Now, sometimes you'll see this on hardware RAID controllers like the PERC and the LSI controllers that we've taken a look at, have this background read patrol thing. And they do that, but again, that relies on the hardware functionality of the drive. The controller is asking the drive to do a full drive read patrol, which is basically a full read of the drive, and the controller makes sure that the drive says that it was able to read everything okay, which most of the time the drive is honest, but there are times where the drive is lying through its teeth. So I'm going to take that with a grain of salt. Now, earlier I asked you what happens when one of the drives is lying, and we sort of talked about that a little bit, but BTRFS and ZFS, because they also store extra data whenever something is written to them, they're able to sort of tell when a drive is lying. They will store extra checksums like MD5 sums. So we've computed the MD5 sums of the files, and these file systems will automatically store extra error detection and correction information in order to recover from that. And that's why those file systems need awareness of the devices that underpin the file system. And so with ZFS and BTRFS, you would not want to use a RAID controller or a RAID situation and then present a bunch of drives as one large volume to the ZFS or BTRFS format. It will totally let you create a 1 drive 1 volume ZFS file system, or a 1 drive 1 volume BTRFS volume. But because the file system doesn't have any knowledge of the underlying file system, you're not going to get any redundancy. If something happens to one of the underlying drives, you're entirely at the mercy of the RAID system for the recovery, which is bad for the reasons that we've outlined. You need to rely on the file system and the file system functionality in order to do that. And so with BTRFS, when you create, it's kind of funny, they're going to change this. They haven't changed this yet, but mark my words, they're going to change this. With BTRFS, when you create a 2 drive RAID 1 and you ask how much free space you have, it reports the actual free space, which is the combined free space on both drives. It's just that when you go to write, like if you've got a 500 megabyte file and you write that to your drives, the amount of free space will go down by 1 terabyte, double that amount. because BTRFS is sort of transparently in the background taking that 500 meg file and writing it to both drives. No RAID controller, no other RAID controller on planet Earth works that way. And some pedantic programmer somewhere was like, oh yeah, this technically you have that much free space, and if you want with BTRFS, you can write the file in a non-redundant way and save some space. That's totally fine, because BTRFS has all sorts of cool things planned, like being able to write a file in a non-redundant way so that if you lose it, it doesn't really matter. But that's just, there's just some crazy stuff planned for BTRFS, and if they actually implement all the stuff that they have planned, it's probably going to have more overhead than ZFS. But that's a video for another time. Oh, and incidentally, if you do run BTRFS on top of MD, and you do want the data redundancy thing, if you do specify the BTRFS data redundancy flag on the command line, you're also going to have half your available space, because for every write that you do on that, Linux multi-device volume, BTRFS is going to write it twice for redundancy reasons. Now, normally by default, it's writing the metadata redundantly, and so that's like the file allocation tables, or like the accounting records of where all of the files are on disk and how big they are, and that is not very much of a space penalty. And the redundancy that you get for that, because if you have drive corruption and it's in a file, oh, it's bad news, you lose the file. If you have drive corruption and it happens to be in an area where metadata is stored, you're going to lose a lot more than just one file. And so that's why this particular file system, BTRFS, ButterFS, stores by default multiple copies of the metadata. It does not by default store multiple copies of data, especially on a single volume or single drive instance, because that would be silly. So that's part one of this series. Part two, and we may split it out into more than part two, but part two is going to be step by step how we tested, how we computed the MD5 sums using the scripts that are posted on the website, and how we introduced a little bit of corruption into the array. Hint, hint, it was with DD, which DD is awesome, and what the results were of each type of test. We actually probably could split the results of each type of RAID test into its own video, but I think we'll probably end up just doing it in one really quick video and then maybe do a longer write-up. And so this has been sort of a backgrounder and an overview of what we've done so far and what the plan is. If you spot a problem with the plan, let me know. I think it's a pretty good plan. And if you learned something, let me know. Or if you didn't learn anything, let me know that too. I'm still getting the hang of this, so sort of let me know what you think. And if you work in the enterprise and you deal with enterprise systems and you learn something, definitely let me know. So, cool. Well, see you in the forums, techsyndicate.com. See ya.